So this chapter is about dimensional analysis. It's really about starting with the concept of collecting experimental data, organizing the data, presenting the data, and then how you would use that data to in design and analysis purposes later. So we go back and it's all about dimensions. So we go back and review dimensions and units. We'll talk about dimensional homogeneity. These concepts are in so many textbooks at the beginning of physics and statics and dynamics and all your typical textbooks in engineering and sciences. Chemistry textbook, it's in there. So please make sure you understand that. And then we talk about if you make an experiment, often you scale it down. So you have a model that's maybe a fifth of the scale of the prototype or the full scale device. So you can scale the model down, maybe use different fluids, make sure that you have similarity between the geometry, the fluid flow, and the pressure and forces. And then you can then extrapolate those results to other systems, larger systems, the prototype, so similarity. And then we'll talk about Buckingham pi. It's a procedure for identifying dimensionless groups and coming up with correlations, or the form of the correlations. A little bit about experimental testing, and then incomplete similarity. So can you extrapolate sometimes the results? And yes, you can. True or false, experiments are expensive. They're very expensive. Experiments are very expensive. All right? So, I'm sorry. Experiments are inexpensive. That's false. Maybe I should have, yeah. They are very expensive, okay? All right, let's go to another one. Experiments are needed.
Yeah.
True. I mean, in a few more years, experiments will become obsolete and computer models will be sufficient for design and verification of new products. And some people have made those claims. People have made those claims, like our computer models are getting so good that we can dispense with some experimentation, and that's a little dicey. You might be able to curtail it some, but you'll never get rid of it. And computers have helped. Bottom line, dimensional analysis is all about measurements. It's about experiments. It's about guiding what measurements to make or to take, and then how to organize the data in the most compact, typically dimensionless form in correlations, and how to then use those results to extrapolate to a system that you didn't test. Maybe you tested a scaled down model so you can predict the behavior of a full scale piece of equipment. So we start with the review. We have 7 primary fundamental dimensions. What are they? Here they are. You also have the symbols for them we use in equations. And then we also have the SI unit for them. Often I will confess, I will say units when I mean dimensions. Or I'll say, give me the dimensions of something. Dimensions are things like length, time, temperature. Units, SI units for length, meter. SI unit for time, second. SI unit for temperature, Kelvin. But this is the general parameter. The general parameter. This is how it's represented or measured with the quantity. There's many secondary dimensions, but can all the secondary dimensions be busted down into the 7 fundamental building blocks? Yeah, they can. They all can be busted down. So here is acceleration. What is it? And bust it down into its fundamental dimensions. Can you do that? I'll pause and see how far you get on that. All right, so going through the list, you can put dimension right here, and then you can put SI unit over here. And so for acceleration, it's length divided by time squared. Maybe you use lowercase t for time, maybe cap T for time. Different books have different symbols. Let's go back to here. What do they use for time? Lowercase t. What do they use for temperature? Uppercase T. Sometimes they use theta for temperature as a symbol. You could check your textbook. What do they use? Mount, maybe some book uses A, some book uses N. All right. So, or you could spell it out. You could say length divided by time squared, right? Okay. And then SI unit, meter per second squared. All right. How about density? Well, that was a symbol rho. That was mass per unit volume, right? So it turns out to be mass per length cubed. True? And then maybe you want to do kilogram per cubic meter. Maybe I put a bracket to emphasize those are my units. Pressure, think Pascal, Newton per meter squared. Keep breaking it down. Newton, kilogram, meter per second squared over meter squared. Looks like it's going to be, put it in SI, kilogram divided by meter second squared. You got it? Pretty good. And then over here you can, I like to work, as you can tell, in SI units. When it gets complicated, you just start breaking it down to kilograms, meters. Otherwise, you got to spell it out. It'll be mass divided by time squared, and then length squared. Specific heat, constant pressure. Length is just by itself, you're right. What about specific heat, constant pressure? How many people got that one? You did? You did? Let's do this. Work on specific heat, constant pressure, specific weight, and viscosity. Mu. Okay, so, and if you want, just do it in SI units. Okay. So for those that did the specific heat, they just sat there and said, oh, I remember the units were kilojoules per kilogram Kelvin. Isn't that how you started? You say, well, if you didn't remember that, you're going to be dead in the water, right? You got to start somewhere. And then you start breaking it down. The joule is Newton meter, so you can get rid of that. And then the Newton is a kilogram meter per second squared, so you can get rid of that. And it looks like we're pretty well there. Let's make sure that this is a cap K for Kelvin, right? Pardon? Oh yeah, get rid of the kilogram. And it looks like we have meters squared divided by second squared Kelvin. What happened to the kilo? You're just chasing units. It's a factor of 1,000 with no dimension or units. All right. So there you go. Thumbs up. You agree? Let's do the specific weight. How do you want to do that? You got to remember something about it. You can do it. Let's say it's kilograms per meter cubed. G was 9.81 meter per second squared. So it looks like it's going to be kilogram per meter squared second squared. The SI. And then the viscosity. How anybody do viscosity? Did you guys do it?
I did it, but I don't know if it's right or not.
Okay, what is it?
1 over rho.
No, got to think. Well, okay, you can go back to equation you remember viscosity is used in. What equation was viscosity used in? Newton's law of viscosity. So maybe you recall tau equal to mu du dy. If that equation is not right, you're not going to get the right answer, right? So is that equation right? So then you say mu is equal to tau divided by, I'm going to put it like this, du dy, because really that's what that derivative is. It's a change in something over the change in something. So now, what are the units of tau? So I'm going to say the units of mu are the units of tau times the units of dy divided by the units of du. What are the units of tau? What is it? It's like a pressure. It's a shear stress, right? It's like a pressure. So it's just like a, I didn't think we did pressure already. So you could just say, I'm going to substitute that to be kilogram per meter second squared. We already did pressure. What about dy?
Meter.
It's a meter. It's a length change. What about du? It's a velocity or speed, so it's meters per second. Meters per second. And so we can maybe get rid of that meter, get rid of 1 second, and then we're left with a kilogram per meter second. One way of doing it. What's another way of doing it? Go to the back of the book and look at a header of a table that has that property listed. And if you look in our book, I think you'll find that they put kilogram per meter second as the units for the properties for viscosity. Okay? You have to get good at that. Dimensional homogeneity. This is in all those textbooks too. Only quantities with the same dimensions can be compared or equated or added or subtracted. That's it. You can't, if they don't have the same dimensions, you can't compare them, right? What is larger, 1 mile or 30,000 seconds? A mile or 30,000 seconds? What's larger? You can't. They had the wrong dimensions. They're not consistent, right? So that's what they talk about, compare, equate, right? As well as add. Add 1 mile in 30,000 seconds. I don't know how to express that. It's not expressed right. Examples, Bernoulli's equation. We had the pressure. We had the 1/2 rho v squared. We had the rho gz. All of those add up, and that's a good equation. Each term has to have by itself the same units as the others. Pressure, pressure, pressure. We gave this a name. This was called the velocity pressure or dynamic pressure. This was given a name. Hydrostatic pressure. And this would be like static pressure. Okay. So you see that all the time, and you've been introduced to that. Go look at the chemistry book. Go look at the introductory physics book. Go look at statics book. They all have it explained in them at the beginning, first chapter. Let's take a look at what I have here. Which of the terms are not dimensionally consistent with the other terms in the list? Is it A or B or C or D or E? Don't shout it out. Let everybody work on it. 4 of the 5 are consistent. 1 is the oddball. Which is the oddball? All right, so the consensus is B. And you really just have to start slugging through it. Sometimes you can look around and bounce around for the pattern. Maybe you remember from thermodynamics that a Pascal times a meter cubed. It's like when you integrate PdV, that's work, true? And then that would have the same units as joule. And a Newton meter, what is that? A joule. So then I quickly narrowed it down to 2 oddballs that I need to work on individually to see which one is the oddball, true, right? And this one is consistent with a joule. This one's not. Did that help? Yeah. Velocity profile is given by the equation. So think of a pipe. You have the center line of the pipe, and you have the radius going out. And so the velocity going down the pipe has this profile. It's highest in the middle, and then it goes out. So this equation is u is equal to a constant a plus a constant c times r squared. So the velocity is a function of the radius, measured from the center line going toward there. Okay, so u is the velocity, r is the radius. What are the dimensions, and then what are the units, the SI units of the constant a? I stop, I pause, we'll walk around and see what you get. All right, so everybody pretty well agreed that the dimensions are going to be length per unit time, and then the SI units, meters per second. True? Good. Okay. What are the dimensions of C, the constant C, and then what are the SI units of C? I pause, I walk around, I see how far you get on that one. All right, so the dimensions and the SI units, we have 1 over meter second, true? And so express the dimensions would be length to the -1, time to the -1. That way you can do it, or spell it out, whatever you like. True? Okay. Flow over a rectangular weir is predicted by the following equation, where Q is the flow rate in meters cubed per second. G is a gravitational acceleration. G is 9.81 meter per second squared. H is the head in meters. So that's in meters for the head. What are the SI units of the constant B? Oops. All right, so this is the way I would do it. I would say rewrite the equation that B is equal to Q. I would drop off the constant 0.67, and I would put divide by, or I'd put G to the 1/2 and H to the 3/2, something like that. So what it really is, I'm saying the units, SI units of B, are equal to the SI units of Q divided by SI units of G to the 1/2, SI units of H to the 3/2. True? Just so far look good? Now I substitute and I say, okay, this is meters cubed per second. And then I have G, that's meters per second squared. But I have that to the 1/2. So this becomes just S. And then I have H, which is meters to the 3/2. So far, so good. And then this is going to be meters cubed over S. I'll pick up the S from below, and then I'll have meters to the 4/2 squared. They cancel. Oh, it looks like it boils down to just meters. Good. So there you go. SI units of B are just meters. Sometimes you can start with an equation. So we want to be able to do that as well, and cast things in dimensionless form, or non-dimensionalize the equation. This is a really simple one. I think I'll just, in the interest of time, talk and you listen. But if we wanted to predict the time that it takes for an object to fall a distance s in a fluid, neglecting viscous drag and buoyancy, it sounds like it's falling in a vacuum. It is. Okay. But I was anticipating saying, now include some viscosity and include some viscous drag, but not today. Okay? We can do that later. But so if I have an object here, and I'm going to drop it to the ground, I release it at rest, it'll fall and it'll hit here. How long does it take? Give me the time, predict the time as a function of something like, oh, the distance that it falls, S, okay? And I know that we're not going to change gravity, but maybe you need to include it. It's going to depend on gravity, right? If I do go to the moon and I have the same object, the same, does it strike at the same time, or does it take longer to fall the same distance if I go to the surface of the moon where g is different? I don't know, right? But we want to develop an equation. From dynamics, you sit there and say, I have the force acting on it, which is only the weight. That's it. There's no upward buoyancy force. There's no upward viscous drag force. It's just weight down. And so the only force acting on it will cause it to accelerate downward. I'll put the scale like this, x going down toward the ground. Okay? And so what I have is I have mg is equal to ma. You notice I really didn't need to put m into the equation because it's going to cancel right now. The mass of the object is not going to be relevant in this model. And we get that g is equal to dv dt, which is dx squared dt squared. And now you solve for it. If you want, you get x equal to where you release it. If you release it with some non-zero velocity, those are two initial conditions. And kind of remember that equation from dynamics? But here we are going to say we release it at a height, or we want to know when it travels to get s. We'll release it at 0. And it has 0 velocity. And it's acting in the gravitational field. So the time t that it takes to strike is 2s divided by g square root. Did I do that correct? So here I have a simple analytic expression. We derived it, and now we could say, oh, I could now cast this in dimensionless form. It seems almost ridiculous, but let's try it. We know that t is units of time, but if I took t and I introduced t star, a new variable, t star, it's going to be a dimensionless time. It's going to be defined as t divided by the square root of s over g. Would that work? Would that now be dimensionless? And then I could rewrite my equation, my analytic expression, say t star is equal to the square root of t. Don't applaud. It's not that big of a deal, right? Okay. Somebody else says, I want to define t star as t divided by the square root of 2s divided by a g. Can I do that as well? Sure. And then t star is equal to 1. Get into the habit of getting an analytic expression and then also cast it in dimensionless form. Let's move on to another problem. Contaminants are a concern for indoor air quality. Consider a contaminant source of strength S, where the units on S are kilograms of that contaminant per second in my room. In the room of volume V in cubic meters, the concentration of the contaminant, kilograms of contaminant per meter cubed of the air in the room, depend on the volumetric flow rate in meters cubed per second of the air entering and leaving. So you're bringing in uncontaminated air. It comes into the room, it's well mixed, and so there's some contamination now, and that is leaving. So if I bring in so many meter cubed per second of uncontaminated air, I have to take out the same amount of meter cubed per second of contaminated air. All right. The differential equation describing the mass concentration as a function of time is here. So this is some accumulation depletion of the contaminant in the room. It's going to accumulate because you have a positive source trying to spew out the contaminant. You also have it being removed with the volumetric flow rate of the outgoing contaminated air, taking with it the concentration of that. And the last term, it's a sink because of negative sign or removal due to being absorbed into furniture, carpets, walls, something else that's in the room. So the last term in the equation accounts for the contaminant being absorbed in the room furnishings, and you talk about the area of the surface in which it can be absorbed and the absorption coefficient KW. KW right there. What are the units of KW? So what do we got? A lot of people said it was meters per second SI unit, right? How did you determine it? Who got the answer first? You two. How did you do it? So basically you can use dimensional homogeneity, and you know that this group has to have the same units as that group, and that group. They all have to have the same units. The most simple one is S by itself because I told you in the problem statement what the units of S are. So each of those groups have to be that. So I know that the units on S have to equal the units on C times the units on the AS times the units on KW. So the units on KW are going to be the units on S, which is the units on S, kilograms per second. The units on area, divide that so you get that it's meters squared. And that's it. No, C, I left off C, which is concentration kilogram per meter cubed. So the kilograms go, and 2 of the meters go, and you're left with meters per second. Is that a good paraphrase? Good. All right. Even better, huh? Well, don't want to. Now, the next part. The maximum mass concentration that is not harmful is C lim, the limited, okay? So rewrite the equation in dimensionless form and identify.
You had an issue with the mouse?
Not me.
Okay.
Somebody else may have. You can check it. It's right here.
Okay, it wasn't jumping around on you or anything?
I didn't. I'm
Okay.
not using it today.
Not your clocks, then I thought that.
All right. Okay, rewrite the equation in dimensionless form and identify dimensionless groups. Something new. Can you do that? All right, so let's do this. Let's take our equation, and all you do is on your equation, you basically divide everything or multiply by 1 over C limit. Okay, so if I put the volume and I divide by the CLIM, the limit, then I have dC dt, okay, equal to S divided by C limit. And then I have minus AV, the volumetric flow rate, C divided by CLIM. And then I have minus C divided by C limit, ASKW. Are all of those terms now dimensionless? No. Which term is obviously not dimensionless? The third term. What are the units on the third term? Volumetric flow rate. How about this? I'll not only divide by C limit, I'll divide by the volumetric flow rate. The volumetric flow rate. The volumetric flow rate. And the volumetric flow rate. Now that I divided by the volumetric flow rate, is each term in that equation dimensionless? I'm going to pause, I'm going to walk around, and I'm going to have you answer that because it's an important question. All right, so you can see that this term right here is dimensionless, and all the terms, because of the concept or the principle of dimensional homogeneity. And what I did to one of the 4 terms, I did to every one of the 4 terms, true? But let's make them look dimensionless by introducing new names and calling things certain things. So what we'll do is we'll call C asterisk. I think it'll be C divided by C limit. Does that make sense? And now, if C asterisk is above 1, I'm exceeding the maximum allowable, maybe by the regulation or the code, laws or something. If it's below 1, I'm not exceeding it. All right? So C asterisk tells you, oh, am I above or below the limit? Let's take a look at another one, S asterisk. It's the source strength divided by C limit AV. Doesn't look all that exciting, but what we've done is we've rewritten this term and this term. Okay. We can also see that this is C asterisk times, and I can introduce another one, area asterisk, which is ASKW divided by AV. Is A asterisk going to be dimensionless? Sure is. And so this will be A asterisk S. I come over here. What I'll do is I'll do this in 2 steps. I'll say derivative of C divided by C limit divided by time divided by volume of the room, AV, volumetric flow rate. And really what that is C asterisk divided by T asterisk, where T asterisk is defined as the physical time times the volumetric flow rate divided by the volume of the room. So I have dimensionless time, and there's my equation. So there is my physical equation re-expressed in terms of dimensionless quantities. And here are my 4 dimensionless quantities. All right? Make sense? Most of the time you don't start with an equation. You don't have an equation. You have to do non-dimensionalization without an equation. This is really getting back to experiments. So in experiments, you will try to do some experiments cover a wide range of the physics. A lot of times you'll do a scaled model, an experiment with a model that's 1/5, 1/10, 1/2 size of the full-scale prototype. And so what we'll talk about is the length of the model compared to the length of the prototype. We'll talk about the speed at some location in our model of the fluid compared to the speed at the same type of location of our fluid at the prototype. We'll actually get to Reynolds number of the model and we'll compare it to the Reynolds number of the prototype. Okay? See how you start matching things up. To be able to extrapolate, you have to have similarity. You have geometric similarity. Think of dimensions. If I'm going to change these dimensions, all the dimensions scale by the same amount for geometric similarity. Kinematic similarity, think of velocity. If I have the flow around these corners and edges, it doesn't have the same velocity, but they have to have the scaling is the same in the velocity field. And the same is true for dynamic similarity. Force or pressure has to scale appropriately. All 3 of those give you complete, perfect similarity. You get 2 of the 3, well, maybe you can still use the results, but you have to be careful. So how do I do this when I don't have an underlying equation? I do it by Buckingham pi method, or the method of repeating variables. It's described in the textbook on pages. I'll give you a very short version of it and then we'll apply it. So you list all of the variables that are important. You count them up, there's n of them. N is 2, n is 5, n is 7. Each one of these you have to say, is it important or is it not important, right? Okay. Then you determine the primary dimensions of all of those n variables. And you count them up, there's j of them. J is typically 3. 3 for mass, length, time. Every now and then you get mass, length, time, temperature. That would be 4. So every now and then you get mass, length, time, temperature, amount. That'd be 5. But almost all, a large number of our problems, it's 3. But you have to count them up. Then you can say this is the number of pi groups or dimensionless groups. It's n minus j. So k is the number of pi groups you look for. So if you're looking for k pi groups, select k parameters to build your pi groups around, and the other parameters that you didn't select, let them help you create them by using them to be repeated in the groups. All right? All right. And then you just make them dimensionless. Once you've selected the ones you want to build around, make them dimensionless. Ready to solve a problem? Yeah? You sound good? Ready to do it? Here's a problem. The drag force on a sphere depends on fluid velocity that's going around the sphere. It depends on the fluid density of the fluid viscosity and the diameter of the sphere. I want you to develop a relationship between F and these other variables in a dimensionless form. All right? So what we do is we start and we say, list all of the variables, all of those important parameters. So what's the first one? Drag force. What's the second one? Velocity, mass density of the fluid, viscosity, and diameter. Now this is the tricky part, but you got to draw the line and say anything else. How about the month of the year that the experiment's being run? Irrelevant. True? The color of the fluid? Irrelevant. Got it? Now if I said some dimpling on the sphere, may not be irrelevant, may be very important. I would have to then put in some scaling for the dimpling or the surface roughness of the sphere, like a golf ball. Very important. All right. But right now, we'll just say that n is equal to, count them up, 1, 5. N is 5. Now we express each of those in their primary dimensions, and I'm going to say dimensions, but I'm going to do it in SI units. All right? So what about force? It was Newton, which is a kilogram meter per second squared. So already now when I see 3 of them, I got a mass, I've got a length, and I've got a time. Let's go to the velocity, meters per second. I see 2, length and time. What about mass density? Kilogram meter cubed. I see 2 more, but they're repeated, right? And then viscosity. Do you remember that one? Mass, mass in kilograms per meter second. Was that right for viscosity? And then diameter. If you've struggled with any of these, here's your chance to rise and shine. Diameter? Meter. Now we count up. How many of the fundamental? You can't get more than 7. How many do we get? 3. 3 for mass, length, time, right? Okay. Now how many pi groups do you expect? 5 minus 3? 2. The way I do it is I pick the ones I want to build my pi group around, and it takes a little bit of experience, but I look at it and I say, well, I'm interested in expressing that in terms of other things. I better build a pi group around my drag force. And the other one I look at and I say, just from experience, it looks like I'm going to cough up a Reynolds number. And the way I look at building a Reynolds number is I pick viscosity. Doesn't have to be, but there you go. Play with it. Pick some other 2 and try it out, okay? Sometimes you can get stuck, okay? A lot of times it's best to pick your most complicated parameters. Which are the 2 most complicated? They have the most of the primary dimensions in them. Well, density has 2, but force has 3, and viscosity has 3. So I picked 3 and 3. All right. I think if you pick diameter and velocity, it doesn't have mass in it. You're stuck. You're going to be a dead end. That's my guess, but I'm not going to pursue that. What I'm going to do is I'm going to say those. So which ones are going to be able to be repeated to make the groups dimensionless? The other 3. So let's go ahead and build around the first pi group, which is I'm going to start with f of d. And I like to personally work with below it, like a line below it, to say f of d is kilogram meter per second squared. I know the book is very algorithmic and they have all these a, b, c, d coefficients and exponents and all that. You can do it and you find a is 0 and b is -2 and c is 2 or 1, but you can do it this way. It'll work most of the time. Now, if I want to get rid of this kilogram, it doesn't look like I'm only going to be able to use v, rho, and d. Rho is the only one that has kilogram in it. I better get rid of that kilogram right away. Okay? So guess what I do is I divide by rho. When I divide by rho, I chase my units. It's a kilogram divided by meter cubed, and kilograms are now gone. Now what is the next most complicated? It's either time. Now I've used rho. Don't use it again. Okay? If you do, it'll bring back mass. Don't use it again. So now I have length and length, but I have length, only time is in V. See that? Seconds are in V. So let me use, to get rid of seconds, let me use V now to get rid of seconds. And then I'll clean it up with D if there's any units of length left. So what do? Is I've got seconds squared right here, right? If I put a v squared, is that a meter squared per second squared that I just introduced? And does that get rid of the second squared? Good, very good. Now I look at it, and it looks like I have meters to the 4th in the numerator and meters squared in the denominator. Looks like I can put d squared in the denominator, and that will give me meters squared, and that'll be, all these meters will go. True? I've built my first dimensionless pi group. Here it is. You know that dimensionless pi group is so often found in engineering that they give it a name. They give it a symbol, not just pi 1. They give it a name and a symbol c sub d. The drag coefficient. Drag coefficient. Okay? Drag coefficient. Let's get the other pi group. Let's get the second one, pi 2. Let me try and tuck it in right here. Pi 2. I'm going to start with mu. But do I have to start with mu in the numerator, or can I start it in the denominator? I can start it in the denominator. It doesn't matter. Numerator or denominator, right? Okay. But once you define and give it a name, the drag coefficient is defined like that. Okay. Not the inverse. It's that. All right. So I chase and I look at my units, and it's a kilogram. Oh, I didn't leave enough room. It's a kilogram divided by meter second. I can use rho to get rid of the kilogram. True? How would I do it? Would I multiply by rho? If I multiply by rho, whoops, I messed that up. It's meter second per kilogram. If I multiply by rho, it's kilogram over meter cubed. The kilograms are gone. True? Follow it? Then what we do is we probably use V to get rid of seconds. So if I multiply by V, that's meter per second, and I got rid of seconds. I look at my lengths. I got meter squared divided by meter cubed. If I multiply by D, the last one, what do I pick up? I pick up a meter. That's a meter cubed divided by meter cubed. I'm dimensionless. So I look, my pi group is rho VD over mu. That one's given a name too. It's the Reynolds number, and sometimes I subscript the Reynolds number. Not E is subscript, E isn't subscript, but D. D saying the length scale in this Reynolds number is diameter. RED. So what we conclude is that you can look to express your experimental results as the drag coefficient, C sub D, as a function of the Reynolds number. That's it. It's kind of like 1 to 1. Give me the Reynolds number, I'll give you the drag coefficient for a sphere. Right? For a sphere. Smooth sphere. Not a heavily dimpled or rimpled up sphere. All right? So, a lot of times what they'll do is they'll plot the drag coefficient as a function of the Reynolds number. They'll get a bunch of experimental measurements, and they'll curve fit the experimental measurements, and then they'll use that one curve fit, plot it, put it in the textbook, and then if somebody else has a similar case, they want to know the drag coefficient on a sphere or drag force, boom, there you go. Okay, very good. A stirrer mixes chemicals in a large tank. So we have a tank, and we have a shaft coming down, and it stirs up the chemicals, and think about some fluid like this in there, and it's being mixed up. We have the shaft power, W dot, the shaft power to drive this stir. And what units would be W dot? Kilowatts or watts? Okay. Which is a joule per second. Okay. The blade D for the stir, maybe meters. The liquid density rho, kilogram per meter cubed. The liquid viscosity mu, what did we like for units on mu? Kilogram per meter second. Sometimes it helps to just memorize something, often by repeated use, and sometimes just by forcing it in your brain. Right? You memorize it, but you got to get it right, right? Okay, now. And then the omega is the rotational speed to angular velocity. Rotational, angular, what is the angular velocity, units of angular velocity? What is it per second? Radian. And is a radian, think about you're back to your primary 7. Is a radian in one of the primary 7 or what? Radian is dimensionless. It's dimensionless. It's a length over length. So omega is just 1 over s, 1 over second, 1 over time. That's it. Okay? So now develop a relationship between the shaft power and the other variables. Well, we'll use the Buckingham pi method. And I first have counted up 1, 2, 3, 4, 5. So how many variables do we have? N is 5. I bust them into the most basic units. I've got to get them into prime. Okay, I suspect there's 3. Okay, but let's go ahead and break them into the most basic. So what is a W dot? What is that shaft power? If you want, you put at W dot SH for shaft power, just to know, what it is. So it's joule per second, which is a joule is a Newton meter per second, which is what? Kilogram meter per second squared meter second. Am I doing it right? So is it squared cubed? Good. There you go. So the rest of this is just work, and we can just write it kilogram meter squared per second cubed. What about D? That's fine. How about rho, kilogram meter cubed? That's fine. Mu is fine, and omega is fine. All right. So now we look and we count them up, and we do find 3 like we suspected. So how many pi groups do we expect?
3,
2 pi groups, and we definitely want to build 1 pi group around this one, and then you have to pick the other one. All right. I look to see which one has the most complicated units. Looks like mu. Looks like mu. I'll build it around there. Okay, so let's go to the first pi group, pi 1, w dot sh. Okay, I'm going to write below it that it's a kilogram meter squared per second cubed. I can only use d, rho, and omega. Yes. Because it has 3 of them, kilogram, meter, and second. If I picked omega, it would probably, I'd get all balled up and I wouldn't be able to do it. Right? I'm not saying I would for sure, but pick something more complicated and then work to simplify it. Okay. So now let's take a look at I only have kilogram and rho, just like we did before. Let's use rho to get rid of the kilogram. And so if we want, we divide by rho, which is a kilogram per meter cubed, and we say goodbye to the kilograms. Done. But you can't use rho again anymore either. I look at it, and I have d in meters, and I have omega in 1/seconds. Easy. Doesn't matter which one I use first. D is only going to handle the length, and the other is only going to handle the seconds. So if I divide by d to the 5th, does that do it for the meters? Sure. And so you get meters to the 5th, and we say goodbye to all of those. And now seconds cubed, do I need to divide by omega? And divide by omega cubed, and then it'll be s cubed, and away we go. So the first pi group is w dot shaft divided by rho, diameter to the 5th, omega cubed. I don't recognize it as a Reynolds number or any other Euler number, Weber number. You can look at, there's different dimensionless groups already people have coined names and stuck names to. It's not a drag coefficient, but there you go. Now let's do the second one, pi 2. What do we start with? Mu. I like to start with probably 1/mu. May show up like a Reynolds number. Okay, so it's going to be a kilogram divided by, or meter second, like this, right? Did I get that right for 1/mu?
Yeah.
Okay. Use rho to get rid of. We've done this before. So that's a kilogram per meter cubed. Say goodbye to the kilograms. Very good. And then either one, let's put in the d right away. So if we put in d squared, that will be meters squared. That'll get rid of all the meters. And then if we multiply by omega, omega is 1/second, and that will get rid of the seconds. We're now dimensionless. So our second pi group is just as expressed. So what we say is we expect w dot sh divided by rho d to the 5th omega cubed to be a function only of rho d squared omega divided by mu, that dimensionless parameter. So I can unravel it a little bit, and I can say w dot shaft is equal to rho d to the 5th omega cubed times that same function, rho d squared omega divided by mu. Both of these would work. I probably prefer the first form because it's truly dimensionless. That's a relationship between the shaft power and the other variables. Make sense? Okay. For creeping or Stokes flow, sometimes they'll say it's Stokes flow, sometimes it's creeping flow. It's the same description, you know, slow flow. The drag force on a sphere moving slowly through a fluid depends on the fluid velocity, the fluid viscosity, and the sphere diameter. So here's my drag force. It depends only on V, mu, D. What was left out? We did a sphere before, but it was a sphere that wasn't creeping flow. There's no rho. There's no density. Let's see how that affects it. But this is now only for a sphere in a slow-moving fluid, or a quiescent fluid with a sphere moving very slowly through it, either one. Develop a relationship between the drag force and the other variables. So how many variables do I have? 4. So what was that? N equal to 4. And we busted into our parameters. We've done this before. So this was kilogram meter per second squared, meters per second, kilogram per meter second, and meter. So it's 3. So how many pi groups are we looking for? So what was it? J is equal to 3. K is equal to a whopping 1. All right. So if it's a whopping 1, what do you want to build it around? Build it around the drag force. So pi 1 will start with F of D. And you can put your units down here. Kilogram meter per second squared. Okay, I'm going to do this. I'm going to divide by mu. That's a kilogram meter second. True? Kilograms go. And now let's get rid of the seconds using V. Let me get rid of that like this. So if I multiply by or divide by V, that's a meter per second. And we're left there. Perfect. This meter goes there. It's so the last one, what I need is divide by D. And we're done. Now, what does this say? It says that the pi group is equal to a constant, which says that the drag force divided by mu Vd is equal to a constant, which says that the drag force is equal to some constant times mu times V times D for Stokes flow or creeping flow. All right. There's one thing I forgot to do. Let me back up and see if I can fix it right away. Sometimes people will put the drag coefficient and they'll put 1/2 right here. Why did they put 1/2 right there? They did change the definition of the drag coefficient by putting a 1/2 there, but they put a 1/2 there because 1/2 rho v squared is also called the velocity pressure, the dynamic pressure, right? And then they'll also do this. Instead of just a d squared right here, they'll put pi and a 4. They didn't really they changed the definition of the drag coefficient, but what is pi d squared over 4? It's the projected area. I have that sphere, right? It's a round sphere. The surface area of the sphere is 4 pi r squared. But the projected area, looking at it this way, it just looks like a disk. That projected area is pi d squared over 4. And so they'll say that the drag coefficient is the drag force divided by the velocity pressure and the projected area. It's a little more readable, understandable.